Hey y'all, it was great to see most of you this afternoon. Um, it is April 1st, and I am starting off with Gabby's question. Gabby asked why uh, number 2 down here was true. And by number 2, I am referring to, for those of you who either haven't had time to watch what we did today or weren't paying attention, or were overwhelmed or were completely zoned out. She was asking how we got step number 2. I don't even feel like it's from step number 1 to step number 2. Like, how did we get step number 2 in general? And the best I can explain, to the best that I can explain it is that even if you look at the first 2 terms, even with just multiplying those first 2 terms, you already have something that's less than 1 over 2n. And as you multiply through, you're going to have something that is even, no matter how far you go in that whole entire multiplication problem, it's always going to be less than 1 over 2n. So I hope that helps. If you still don't understand, go ahead and attend a Zoom session next week. I have my office hours up in Blend. Take care. Bye-bye. I have no idea why I just said bye-bye. Anyway, if you look at the integral test, this is a pretty simple situation. The series would be k equals 1 to infinity of a sub k, and the integral would be the summation from, or I'm sorry, the summa from 1 to infinity, or gosh darn it, sorry, the integral from 1 to infinity of a of x dx. And in order to understand that, you need to remember that the integral is actually just a Riemann sum. So one of them is a Riemann sum, like with very particular partitions, and the integral is the limit of a Riemann sum, the limit where the partitions are approaching, the number of partitions are approaching infinity, where a sub k equals a of k for integers k greater than or equal to 1. If either diverges, so does the other. If either converges, so does the other. So we can also show that our sum is somewhere between the integral from 1 to infinity and the first term plus the integral between 1 and infinity of a of x dx. So no matter what, your sum as from k equals n plus 1 to infinity, which is this k equals n plus 1 to infinity of a sub k is less than or equal to the integral from n to infinity of a of x dx. I really wish I was teaching this in person. Give me a second. Okay, as you process the definition of the integral test, it is really important to remember that an integral is just the limit of the sum. By definition. So that definition of the integral is coming up and coming out of nowhere to remind you what it is. I don't know. I'm having trouble wordsing. Anyway, you come down to the first example, and we have this sum, which we're not going to know the sum of that. So we look at the integral to compare. And when we compare the integral, we see that that integral, in fact, does not have a limit. Therefore, the sum diverges. And if you're having trouble seeing how I found how I integrated this, go ahead and pause the recording and try some USub. But most of you should be able to see that, I hope. In B, we look at that and we see immediately that we can't find the sum off the top of our heads, but we can look at the integral and do a comparison, And when we do that comparison, we see that that does in fact have a limit of -1/2. That n is going to get bigger and bigger and bigger and bigger and bigger. And when it gets big enough, no matter how big it gets, I don't know, I'm having trouble wordsing again. Give me a second to collect myself. Oh, I always forget when I press pause, you don't know I'm pressing pause. So, here we go. So, as it approaches infinity, as n approaches infinity, that whole entire sum is getting closer and closer to -1/2. Therefore, you can say that the sum, not the sum. The integral converges to -1/2, but you also cannot say that the sum of the series converges to -1/2. You have to say that the sum of the series converges. That's all you know. You don't know where it converges to. Understood? Okay. Okay. Sadly, I can't rewind and figure out what I just said. So basically, the integral converges, therefore the sum converges, and you cannot say that the sum converges to the same value as the integral. Those are not going to be equivalent. So I'm going to note that very quickly, and then we're going to move along. This last little bit is, pretty important. Oh my gosh, I can't shrink it. Okay, there we go. Okay. I wish you could ask questions, but I guess we get to save that for the very awkward venue called Zoom. And let me pull in the picture. This is kind of cool. You've never seen me do this before, have you? I hope you can see the whole thing. It's really funky. Okay. Let me see. I think we're right there. No, we're not. We just did that. I need to get rid of that, but that's okay. I don't know why I'm letting you listen to all this, because it's kind of funky, isn't it? Okay, I'm going to push you on pause. So as luck would have it, we can use the integral test to determine the upper and the lower bounds of a series. So we can say that our particular series is somewhere between the original integral and the integral plus 1. So we're going to do that real quick. So once we've established that and written that down, we can say that our sum is somewhere between -1/2. I have it written down incorrectly in my notes. And +1/2. Doo-doo! Easy peasy pumpkin squeezy. In this particular portion, I'm going to be reading you quite a bit of this. I know that that is insulting. I'm not a big fan of being read to, but some of us are auditory learners and some of us are visual learners. So we're going to go through the integral test more in detail. You're going to consider the series the sum of a sub n such that a sub n is greater than or equal to 0 and a sub n is greater than or equal to the next term. That is what is being referred to right here. This is the term that is after a sub n. And because your exposure to this kind of notation is relatively weak, you may or may not understand that, which is why I have clarified with those words. Some of you totally get that, and some of you do not. We can plot these points on a graph and construct rectangles whose bases are length 1 and whose heights are of length a. If we find a continuous function f of x such that f of n equals a sub n, then notice that the area of these rectangles, the light blue plus the purple, is an upper Riemann sum for the area under the graph of f of x. Therefore, the integral from 1 to infinity of f of x dx is less than or equal to the sum, or the upper Riemann sum, of a sub n. Okay. Now notice that the area of these rectangles, oops, I already said that. Likewise, if we investigate the lower Riemann sum, we see that the lower Riemann sum is less than or equal to the integral. Since the first term of a series has no bearing on its convergence or divergence, this proves the following theorem. The integral test says that the sum of the series converges if and only if the integral converges, which we'd already talked about, but now we've proved it. I think I just kind of flat out gave it to you prior to this moment. Also notice that if the series diverges, if one of the two of them diverge, then both of them diverge. There is, as you can see, a link here. I'll try to link it in today's lesson, but I don't know that I can due to time constraints. I'm working pretty much sun up to sundown, not to make you feel sorry for me. That's not my intent. I'm just real limited on time. For the sake of proof, we're going to be working with the particular series n equals 1 to infinity of a sub n. The original test statement was for a series that started at a general n equals k, while the proof can be done for it, it will be easier if we assume that the series starts at n equals 1. So let's start off and estimate the area under the curve on the interval 1 to n, and we'll underestimate the area by taking the rectangles of width 1 whose height is the right endpoint. This gives us the following figure, and as you can see, this is a lower Riemann sum or a right Riemann sum. If you look there, we know that this underestimates the actual area. So the series is less than the integral. Now suppose that the integral converges. If the integral converges, then the integral has a finite value. Also, because our function is positive, we know that the integral from 1 to infinity is going to be bigger than the integral from, say, 1 to n. This in turn, means that the sum, the series is going to be less than the integral from 1 to n, which is going to be less than the integral from 1 to infinity. However, this isn't quite what we need, so we need to start with our first term. So we just add our first term to both pieces. And then we have, so just what has this told us? Well, now we know that the sequence of partial sums is bounded above by m being the first term plus the integral. Because all of the terms are positive, we also know that stuff. Oh my gosh, I don't know if I can say all that. S sub n is less than or equal to S sub n plus A sub n plus 1 equals the sum of A sub k from k equals 1 to n plus A sub n plus 1, which equals the sum from k equals 1 to n plus 1 of A sub k equals S sub n plus 1. And so the sequence of partial sums is also an increasing sequence. So we now know that the sequence of partial sums converges, and hence our series is also convergent. So the first part of the test is proven. The second part is somewhat easier. Let's overestimate the area under the curve. And when we overestimate the area under the curve, we end up with something. We end up with what's written there. I'm just not going to say it all. It seems like such a waste of time. So we know, again, that the integral is divergent. And that means that our integral approaches infinity as n approaches infinity. However, because n minus 1 also approaches infinity, we know that our integral approaches infinity. Oops, that's the wrong slide. There we go. Sorry about that. Okay. I feel really dumb reading to you. Therefore, since S sub n minus 1 is larger than S sub n minus 1 was the series there. It was noted on the previous page. S sub n minus 1 is larger than the integral from 1 to n minus 1 of f of x dx. We know that as n approaches infinity, our series also approaches infinity. This in turn tells us that the sequence of partial sums is a divergent sequence, so the series is also divergent. It is really important to notice that in order to use the integral test, the series terms must eventually be decreasing and positive. If they are not, then the test does not work. So I'm going to highlight that very quickly. Also, remember that the test only determines the convergence of a series and does not give the value of the series. Oh, that didn't work out very well. Let me see what I can do about that. Let's see. I feel like I can't figure out how to make the highlighter B so you can see through it. So anyway, ta-da! Okay, if you have issues with understanding what's going on, in this particular case, I actually recommend Khan Academy or Patrick JMT, because the integral test is actually relatively straightforward. You're just looking at the integral and the series and comparing the two to decide whether the series is convergent or divergent. But remember that you can't find the actual value of the value to which the series converges using the integral test. I will go out of my way to try to link the Khan Academy and maybe even some Patrick JMT for you. Patrick JMT is an ACC professor who teaches calculus at ACC and also writes for several textbooks. Have a good one. See you soon. Take care.